Welcome back to the lab. Welcome back to EEforEveryone. We are continuing our journey discussing current sources, and today we're going to dive into how to build a current source with a BJT, a bipolar junction transistor. It's going to be phenomenal. Let's dive in. All right, so in our previous video, check it out if you haven't seen it, we walked through what a current source is and the fundamental theory behind that. Today, we are going to be kicking that up a notch by designing one. All right, our symbol for a current source is like this, where I is fixed. Excellent. All right, where are we going to take this? Well, one big place. We're going to take this to the mall. No, just kidding. We're going to take this to... we're going to take this to something that we can actually build. Because I don't know about you, but ideal current sources aren't very easy to find on the shelf. And we're going to build one with a BJT. All right, so how do we build this with a transistor? Well, it starts with some kind of voltage source, some kind of power source. It could be unregulated. It's not very important. But then we end up with this RS, we're going to call it. It's a sense resistor. And we're going to say this is a 3906. Which I'm pretty sure that's a PNP, and if it's not, I'm going to feel really bad, but hopefully you forgive me. Pretty sure that's right. We end up needing two things. We end up needing a bias resistor and some mechanism for regulating. In this case, I'm going to recommend that we use a couple forward bias diodes. Why? Just regular silicon diodes. I think there's a 2N, oh goodness, I'm going to butcher that part, but we're just going to grab some regular 0.7 volt silicon diodes. Why? Because the forward voltage of the base emitter junction is basically the same thing. It's basically just a regular PN junction, and so if we only use one diode, we won't be sure that the voltage of our reference is very high. And the reason why we're doing two of these instead of something like a Zener diode is just because, in my opinion, we'll be able to make this a little more consistent across temperature. But it really won't be that great either way. So we're going to do some iterative building on this concept, as you might have imagined. That's kind of our theme these days, iteratively building up larger concepts. So these are just going to be silicon, about 0.7 volt. Okay, so we've got what's basically like a 1.4 volt reference that we've built. We've got this bias resistor, and we've got this sense resistor. Now, these two end up being very important because they kind of like drive the gain or the responsiveness of our amplifier. So the fundamental balance that this circuit is striking is that when this voltage drops below 0.7 volts, approximately, this is very rough, and we're going to run this in the simulation to see how close these rough assumptions get us, but there's basically like a 0.7 volt voltage source here. I'm just going to sketch that in. And then after there's 0.7 volts, we basically have an ideal current source where this is like the gain of the transistor times IB equals the collector current. Super rough. So we can estimate what that current will be. No, that's not right. So basically that's like the sensitivity. That's like the sensitivity of this circuit, how quickly it can respond. But what's truly doing the current regulation is this high side resistor. Because if 0.7 volts is dropped there before our amplifier really starts to move, that's what this transistor is acting as. It's acting as an amplifier. There will be VRS equals 0.7 volts when the PNP is enhanced. Oh boy. I can feel my mind starting to rush. I can feel my mind jumping through this concept. Hopefully all the words are making it out and this is making sense. So basically we will drop 0.7 volts here. We'll drop the other 0.7 volts across the internal diode in our transistor. We'll have some bias current coming down here multiplied by the gain of the transistor, which basically determines kind of our sensitivity, that resistor. And then this resistor will determine our maximum current. Does that make sense? So to plug in some numbers, I'll use a new color just to be clear. Well, if we have 0.7 volts that we're going to drop across our S, what do we want our current source to be? Let's shoot for approximately 1 amp. So knowing what we know about Ohm's law, if we want I to be 1 amp, 0.7 volts divided by question mark equals, what was that, 1. 0.7 divided by 0.7 is equal to 1. So this should be 0.7 ohms. So excited, had to draw a fancy exclamation point. All right. And then this is where we would hang our load. Whatever it is that we want to drive, that is where we would put the load. Since I don't know any better, I know that if we want to pull an amp through this poor 3906 that's going to explode because it's not made for that kind of current, we're going to need to use a different transistor. But our PNP that will be approximately equivalent. Let's say it has an HFE of at least 4. That's a pretty safe assumption. Let's assume that it has at least a gain of 4. That means that at a minimum, we need to have 1 amp flowing through the base of this PNP in order to ensure that it turns on, right? Because this gain times base current equals collector current. That's just how the transistor is going to work. And so we need IB to be equal to approximately 250 milliamps. Okay. Let's say that our voltage source, let's use an ideal source for right now. Let's say that it's 24 volts. 24 volts. If we want about 250 milliamps of current on a 24 volt supply, let's call it 240 milliamps. Right, we should be able to do that pretty easily. It's all Ohm's law. It's all Ohm's law. 24 volts divided by 0.24 amps equals, what is that? 100 ohm? I think that's 100 ohm. Boom! We're there. That was fast. That was the fastest I've ever drawn an LTSPICE in my entire life. So, what do we have? Our reference diodes. We've got our resistor. We've got our load. And the reason why I have a sinusoidal source down here is because I want to force the output voltage to change. I'm forcing the output voltage to change, which for a normal voltage source, that would cause some pretty serious drops on the output. Not drops. That would cause some serious variation in output current. Like, if we were adjusting, you'll see. Basically what you'll see is this is a fairly decent current source. But this is a varying load, right? If it was just a fixed resistor, that wouldn't be very cool. The dynamic performance of the system is a little more interesting. So we've got a voltage source on the input, we've got a changing load on the output, we've got this like bias resistor network. Let's see how we did. Let's hit run. Okay. We're going to look at the current through the load. That looks pretty sinusoidal to me. That actually looks in phase with our voltage source. What gives EEforEveryone? I thought you said this was a current source. Well, we need to keep in mind the scale on the left-hand side. For reference, I'm going to put the current on this bias resistor just to give you an idea of where we are at. So the current through the load, R3. Actually, we're going to rename that. We're going to rename that to R load. We're going to rerun this. Okay, the current through R load. The current through the resistor load, and I'm just inverting that so the plot looks right. Okay, so it looks like there is definitely some variation, but we're right around 1.2 amps. Wait a minute, 1.2 amps. That doesn't sound right. Yeah, we said it was going to regulate to 1 amp. And what did we say? We said that it would regulate to 1 amp if 0.7 volts was dropped across this resistor. But how much voltage is actually being dropped? Let's add another plot pane. Let's remove that trace. We're going to add a second plot for voltage. We want to select this one. Okay. So now, okay, that looks a little bizarre. That doesn't look quite like what we were expecting. That's a little bit more than 0.7 volts. In fact, that's 0.84. Why is that? Well, it's because the forward voltage of this transistor is closer to 500 millivolts in this operating point. Now that's going to be current dependent, output current dependent. So it looks like in this case, it makes sense to have a slightly larger resistor for R1 because it's 510 millivolts instead of 0.7. While we're at it, let's also look at the voltage across this reference. How close are we to 1.2? Well, it looks like we're averaging right around 1.35 volts. Okay, so let's consider this, all right? We're going to use 1.35 since we're taking this around an operating point. This is the operating point that we care about. We know that our reference will be about 1.35 volts. I'm just taking notes here on a piece of paper. We know it'll be about 1.35 volts. And we know that the current through the base of this transistor will be approximately 0.513 volts. Factoring that into the same equation as before, that means that we know that we need to tweak this resistor to 0.837 ohms. Apologies, hotkeys, too many. Okay, and now we would expect that this current, our load, is much closer to 1 amp. Look at that. Sure enough, we are right around 1 amp. Looks like the cursor is reading 1.01. So that's pretty darn close. Okay, so we looked at this operating point. We grabbed a little bit of data. We tuned the circuit. Obviously, there are analytical methods to consider all of these things, but we're not interested in bounding the complete tolerance of the system. We're making an example and explaining current sources, right? This is not meant to be a, here's the perfect way to design the best current source known to man. This is a simple, simplified example. Would this work? Yes, you could build this. It would work. Would it be efficient? No. Let's demonstrate a couple other features of this current source before we call it a day. Now, let's say, for example, it wasn't a 24 volt source. Let's say this source were a little ugly. So let's say that it actually ranges from about 14 volts to about 30. Oh, I need to stop using numbers that... All right, and we're going to say there's no delay. Rise time, we're going to say that's 0.25. And same thing, 0.2 on the fall time. T on, we will say that is 0.5, and the T period, we will say that is 1. So what in the world did we just do? We just changed our voltage source to no longer be constant. Our input voltage is now swinging all over the place, as you can see. And our output voltage is now swinging all over the place because we've got a dynamic load and an unregulated input. Oh, okay. That sounds like fun. And while we're at it, maybe this source has some internal resistance that makes it not ideal. So now maybe we've got a load dependent, oh goodness, we've got a load dependent changing voltage source, and we've got a dynamic load, and oh, how does the current look? Okay, we might have pushed it too far. We might have made that input voltage get too low. I think we're falling out of regulation. Let's make sure I didn't push this circuit too far. Everything has limits. Yeah, and when are we dropping out of regulation? Probably when our input voltage, yeah, okay, so our input voltage goes a little too low. Let's not go down to 14, let's go down to 20 volts. Better. All right, apparently 24 is about the minimum. Okay, yeah, that's much better. So we can give that current the same context. Excellent, that's not too bad. So with an input voltage that looks like this and an output voltage that looks like that, our current source is managing to regulate current fairly well. If this were an ideal current source, what would we expect to see? We would expect to see this as a flat line, the red cursor on the load. We would expect to see a flat line, but that's not quite what we see, and that's okay. This is not a perfect current source. It doesn't have the fastest transient response. It is not the most accurate. It is pretty temperature sensitive. Would this be something that I would build into a full design? Probably not. But with a little bit of temperature compensation, it could actually be pretty great. Temperature compensated current sources are built into integrated circuits because they can be pretty simple. You just need to use a few other tweaks to make it a little better. You can use some current mirrors. You can use lots of techniques to bias the transistor more accurately. But this is the fundamental theory. This is the groundwork. And if I'm being honest, compared to a standard voltage source, this is pretty great. Oh, you don't believe me, you say. You say, no, we want the proof. Okay, I'll give it to you. Here's what I've done. I've added a second source down here. Hopefully you can see that all right. I've added a second source that's just the same voltage source that we had before with the same load that we had before. So our load 1 will be in lockstep. Just to demonstrate, let's compare. Okay, so wow, that is an excellent story if I've ever seen one. So what we're seeing here, this is the regulated source right here. Regulated. And this is the unregulated. If you wanted a constant current source, which of those waveforms would you rather see? Well, we're supposed to be regulating to an amp. We're seeing peaks of almost 3 amps out of the unregulated situation, anywhere from 1.6 to 3. I've got a feeling the load wouldn't like that too much. Yeah. Yeah, that is a huge difference. I hope that you can see the value in what we have done today. It's certainly not ideal. It is certainly not the best current source in the world, so make sure you stay tuned for our next video where we improve this. But before we call this a day, I want to point out the obvious compromise here. We added a bunch of active circuitry. We added a bunch of components. And the penalty for building not only a current source, but a linear current source that outputs significant power is efficiency. If we look at the power burned in this component, you hold Alt in LTSPICE to do this, and we click on that transistor. Okay, let's just clear all the other traces here. So this is the power being dissipated in that transistor. And if you hold Control and click on the title, ooh, an average power of 10 watts being burned in that part. So sure, we have current regulation. Sure, it's happening. It's linear. It's actually probably pretty sweet. But you're burning a lot of power to get it. Is it worth it? Probably. But there are other ways to do current regulation. In the same way that you can build in the same way that you can build switching and linear voltage supplies, you can build switching and linear current regulators as well. So for a power type application, you probably wouldn't do this way, but for small signal current sources, for example, capacitive timers, something kind of like a 555 circuit, maybe something like that would have some use for a current source where you wouldn't be burning 10 watts in your pass element. Pass element is a general word for that transistor. Okay, that's about all I've got for you. I hope that you enjoyed this overview of current sources. If you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, or leaving a comment down below. Coming up soon, we will be developing this concept even further, improving performance, and perhaps even transient response by swapping out this simple transistor voltage source situation for something a little more complex. It's going to be a lot of fun. I can't wait. If you'd like to support the channel, please check out our Patreon page linked in the description. Down there you will also find links to this project for LTSPICE, all of the tools that we're using if you want to follow along at home. Really helps us out a lot. Thank you. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EEforEveryone, and thank you for staying till the end. Bye.